Great, it's recording now. Today, we should talk about section 3.3, power functions and polynomial functions. And then we will talk about the graphs of these polynomial functions. Okay, so first, as an introduction, let's recall that there is a function for the area of a circle with radius r. That function is just a of r equal pi r square, right? Pi r square. Very good, very good. Now, welcome, Lucero. How are you doing? Everything good? Okay. Also, as a function, there is a function for the volume of a sphere, right? Just like this function measures the area of a circle, there is another function that measures the volume of a sphere, and that is given by this: 4/3 of pi multiplied by r raised to the third power, or r cubed, right? Measures the volume of a sphere. Okay, great. Now, when mathematicians look at these two functions, they notice something they have in common. Notice that both functions have up front this constant, this real number multiplying, right? So real number up front, a number. And mathematicians call these real numbers constants, right? Constants. So a constant up front. Right? And following the power of some variable. In this case, the variable is being squared, right? Square. So r squared, power of a variable, right? Power of a variable. So mathematicians notice this, right? Here again, when you compute the volume of a sphere, first 4/3 of pi, this is just a real number, constant, followed by some power of a variable, right? In this case, the third power of the radius of the sphere, right? So followed by power of a variable. So turns out these type of functions appear a lot in science and also in real life situation. Okay, so they deserve to be studied, right? Variable. So mathematicians call them power functions, right? So, and they define these power functions as follows. A power function is a function that can be written in the form f of x equal k, constant, right? Multiplied by x raised to p, some power of the variable, right? Some power of the variable. So here, the constant is given this name, the coefficient. This is called the power, x to the p, power of the variable, power of x, and this p is called the exponent, right? The p, the exponent. All right, now k and p could be any real numbers, okay? Any real numbers. And k is known, as we just stated, as the coefficient, right? The number up front. Now, examples of power functions. F of x equal 2 times x to the third power, or 2 times x cubed, is a power function, right? You see the form here. Some real number up front multiplying the power of some variable x, right? Another example, g of x equal 3 times x to the 4th power, 3 times x to the 4th power. And again, you see the pattern, right? You see a number up front multiplying the power of a variable, right? In this case, the 4th power of x, 3 times x to the 4. Now, we said that this number up front is any real number, so it could be positive, could be negative, right? Another example of a power function, h of x equal minus 1/7 multiplied by x raised to the fifth power. Okay, so these are examples of power functions. Okay, now, welcome guys who just joined. Julie, welcome. Eugene, welcome. Okay, guys, let's continue, right? We're talking about power functions. Now, when you graph these power functions, there is this behavior which mathematicians call end behavior of power function, right? End behavior of a power function. So what is that? It has to do with the way the function behaves for big values of x on the right or on the left. But first, let's just kind of classify or put this power function in two groups, First group, power functions having even exponents, right? Even exponents. Turns out when graphed, they have parabola-like graphs. Parabola-like graph. They look like parabolas, okay? No matter what. For example, right? If you graph f of x equal x squared, we know that this guy is going to show us this U-shaped parabola, right? Opening upward because the coefficient, leading coefficient is 1. Now, what happens when you graph g of x equal x to the 4? This guy is still even, right? So according to this, you should expect a parabola-like graph, right? But turns out this parabola-like graph is going to be flatter here close to the origin and is steeper when you go away from the origin, okay? It's gonna look like this. So let's write it, right? It flattens close to the origin, which is this, right? The origin, close to the origin. Close to the origin, and it gets steeper far from the origin. It gets steeper far from the origin, right? Yeah, but still you can see the parabola-like shape there, right? The parabola-like shape. Let's just kind of do it nicer. I don't want this to look like a vertical line. I want it to look like a curve, but that curve should be perhaps like this, right? Yeah, that's better. Okay, but now for you to see these guys, right? For you to see how this works. Look, I'm gonna use our Desmos graphing calculator. Y equal x squared. This is the parabola that we have here, right? Now let's see the effect of changing our exponent from 2 to 4, Notice, right? The new graph, as we describe here, gets flatter around the origin and then gets steeper as you go away from the origin, right? Steeper, it's this blue graph. Now, if you continue increasing the value of the exponents from 4 to 6 now, notice that it's going to get flatter close to the origin and steeper when you are away from the origin. You can see, right? This green graph, flatter here, is steeper, right? That's how it works. I encourage you to play around with this Desmos graphing calculator for you to confirm these facts, right? So basically, the graph of h of x equal x to the 6, you should expect it to look like a parabola, but very, very, very flat here, very, very flat. And here is steeper than the one before, right? Steeper. That's how it goes. That's h of x equals 6. All right, so this is the first group, right? When the exponent is even, this is what you should get when you graph these power functions. Now, the second group is this: power functions with odd exponents. What happens when the exponent is odd? Turns out the graph will resemble now a chair-like graph. Power function with odd exponent will have chair-like graphs. Chair-like graphs, right? Just like the one with even exponents, they resemble a parabola. This one's resemble the graph of a cubic function, right? So f of x equals x to a third, we know from our knowledge of power functions, for our knowledge of cubic functions, better said, right? That the graph of this guy looks like a chair like this, right? Now, what happens if you increase your exponent from 3 to 5? Well, similar idea, right? Close to the origin, the chair-like graph will get just flatter here, flatter, and is steeper as you go away from the origin, right? So flatter here, close to the origin, and is steeper as you go away from the origin, right? Steeper. And again, guys, use your free Desmos graphing calculator to confirm that. Look, y equal x cubed indeed is this chair-like graph, right? Look like a chair where we sit. Now, if you increase the exponent from 3 to 5, look what happens with the graph. Gets flatter at the center, right? Close to the origin, 0 here, flatter, right? As we showed here, and is steeper. The blue graph is the new graph, right? It's steeper, grows faster, right? Faster as you go away from the origin. So when we graph this guy, h of x equals x to the 7, not a surprise, the chair in shape will appear, but now notice even flatter here close to the origin, and is steeper, grows faster than this guy, right? Yeah, great. So play around with this Desmos graphing tool, okay, and confirm this fact. So this guy should be much flatter. I'm going to exaggerate here, right? And then it should be really, really steep, very steep. So like that. All right. So these are the shapes for power functions with odd exponents, right? Chair-like. Okay, now, what is the end behavior then now? The end behavior has to do with the output values of the function as x increases without bound to the right or to the left, right? To the right or to the left. So it has to do with these arrows, to put it simple, right? For example, for you to understand this idea of end behavior, let's go over this example. It says, determine the end behavior of the function f of x equals x to the fifth. F of x equals x to the fifth has this graph, right? Has this graph. So I'm going to take it from there. I'm going to just do it here. And I want you to observe as x gets bigger and bigger to the right, where the output values are going. Well, you can see that as you go to the right on the input values, the output values go up here to infinity, right? To infinity. Remember, infinity lives here, right? So as x goes to positive infinity, y goes to positive infinity, right? So you can say that f of x rises to the right inwards, right? And what happens when you go to the left? If you let x increase to the left towards negative infinity, now the output values decrease without bound, right? To negative infinity. So we can say that eventually f of x falls to the left, right? Falls to the left. This in words. But mathematicians, remember, they like symbols equivalently. In order to say this and this, mathematicians develop these symbols. And this is something that you have to understand because you're going to need this in calculus. Okay. So look, instead of saying f of x rises to the right eventually, you can say in symbols this: as x, as the input values approach plus infinity, as x approach, or approach is better said, plus infinity, then f of x approaches plus infinity to, right? Goes to plus infinity. And this f of x falls to the left eventually can be expressed in symbols by saying that as x approaches minus infinity, right? This direction, f of x, the output values, they decrease without bound towards negative infinity, right? So f of x approaches negative infinity. And this is what mathematicians call the arrow notation. The arrow notation is this. See these arrows, right? And I hope this is clear. And the end behavior is just this, is where these output values are going here and here, right? This is what determines the end behavior. So let's highlight this, right? End behavior. So for the end, if they ask you what's the end behavior, well, you can say f of x rises to the right eventually, right? And f of x falls to the left eventually. Or you can say this using the arrow notation this way, right? This is the end behavior. Try to remember these guys for your homework. They're going to ask you for the end behavior of some power functions, some polynomial functions. You will see. Great. All right, great. Now, mathematicians in general discover that the end behaviors, they come just in 4 types, 4 forms. What are they? Well, first, if the exponent is even, if the power function has even power, we already saw that the graph will be parabola-like, right? Parabola-like. So it will rise to the left, it will rise to the right. Eventually, right? Eventually. Or using the arrow symbols, this. And this graph that I have here, it's on your textbook. You can, I copy and paste it from our textbook. You can do the same and have it somewhere. It's in our textbook. In the calendar, click on the link that corresponds to the lecture, it will take you there. Now, this is for k positive, right? For the coefficient being positive, right? Because we know that if the coefficient, the number up front is negative, the parabola will open downward, right? Remember yesterday we saw happy face, positive coefficient, parabola opens upward, negative coefficient, parabola opens downward. So this is the second scenario here. If the coefficient k, the constant up front is negative, your parabola-like will open downward. Falls to the left, falls to the right. Or using the arrow symbols, here is what you have, right? As x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x approaches negative infinity as well. Now, the second scenario is this. If the power function has odd exponent, right? Odd exponent, odd power. Well, then you will get a chair-like function, right? When you graph it, you will get something that looks like a chair, and it will fall to the left and it will rise to the right as long as the coefficient, the number of front is positive. But if it is negative, you have to take the reflection of this, right? And you get this other chair-like, but now I call this a decreasing chair-like from left to right. This is an increasing chair-like from left to right, right? And the arrow notation is here, right? For example, here as x goes to negative infinity, f of x, the output value goes to negative infinity as well. As x goes to positive infinity, the y values, they go to positive infinity as well, right? Yeah, this using the arrow notation. Okay, guys, so these are called power functions, right? But now our goal is to work with polynomial functions. So what is a polynomial function? Let's define it so we can go over some exercises. A polynomial function is defined as follows. Let n be a non-negative integer, some whole number, right? A polynomial function, a polynomial function, is a function that can be written in the form of a polynomial, right? A polynomial. F of x equals some number multiplying x raised to n, and then you will get more terms here. Eventually, you will get to a number multiplying x squared, another number multiplying x, and then your constant term, right? This is how mathematicians represent polynomials in general, right? Don't get freaked out when you see this representation. It's just a polynomial in its most general form, right? All right, now, let me give you a numerical example for you to visualize what a polynomial function is, right? Consider this polynomial function, f of x equals 2x to the 4 minus 5x to the third plus 6x squared plus 3x plus 7. The number that appears at front, this guy 2, should be called the coefficient, right? But since there are several terms, right? Mathematicians, they call it the leading coefficient, because it's the one that leads, right? Leading coefficient. It's not just any coefficient, it's the one that is the first one, right? So coefficient, leading coefficient. Now, this guy as a whole is called the leading term, okay, all together. Now, the number on top of the variable is called the degree, this guy, highlighted, degree. Is the highest power of all the terms, right? This has exponent 3, this has exponent 2, 1, exponent 0, but the highest, this 4, is called the degree of the polynomial, okay? And notice that the polynomial should be written always starting with the term with the highest degree, right? This is called the leading term, leading coefficient, and then the rest is written on the right. Now, the degree of f of x is 4, right? We set that 4. Leading coefficient of f of x is the number that appears up front, the number 2. Leading term of f of x is, leading term, the whole thing right here, 2x to the 4. Now you may say, Professor, why you are emphasizing describing completely just the first term? What about the second term, the third term, the fourth term, fifth term? Don't they matter? Turns out they don't matter much. The one that carries, the ones that holds the information for you to determine the end behavior of a polynomial is this term, the leading term, right? So this is a very important term. All right, great. So this will be clear when we go over this fact. Mathematicians discovered that the end behavior of a polynomial function is determined by the end behavior of its leading term. So if you look at the end behavior of this term, this will tell you the end behavior of the whole polynomial function, right? And that is why we have to pay attention to this term, the first one. The others are just followers. This is kind of the leader. All right. So for example, suppose they ask you to figure out the end behavior of a polynomial, of this polynomial function. Minus 6x to the 5th plus 3x to the 4 minus 8. They ask you to figure out the end behavior of this polynomial function, right? So based on the fact, then we quickly pay attention to the first term, the leading term, right? We separate this from the rest. So we can create a new function, f of x equal negative 6x to the 5th, and work with this, right? Don't worry about these other two terms. All right, now we pay special attention to these two numbers. This number up front, negative 6, right? Coefficient, negative, right? Negative coefficient. And then we pay attention also to this, to the degree, right? The degree, odd degree, right? And with these two, we go back to our table, right? And try to remember what is the end behavior of this based on this, right? Odd exponent, odd exponent, and negative coefficient, k less than 0. Look, odd exponent negative coefficient shows this chair-like function, but it's a decreasing chair, right? So this is what you have to consider here, right? So if you draw an XY coordinate system there, and quickly this, then you have to consider something that looks like this, right? A chair-like function, but what I call a decreasing chair from left to right, right? This will be the graph of this guy, right? The one that is the leading term. Now, clearly you can see there that this one rises to the left, right? Rises to the left, right? You can see it from here. And you can see that this falls to the right, falls to the right, right? So there you got your end behavior. Now, if you want your end behavior using the arrow notation, then you have to say, as x approaches, here is where negative infinity lives, right? Negative infinity, then f of x approaches, the output value, look, is going up here, right? Infinity, positive infinity, or just infinity. Similarly here, right? It falls to the right. Equivalently, you can say this using the arrow notation, as x approaches positive infinity, right? The input values go in this direction. The output values, notice they go down here, right? So then f of x approaches negative infinity, right? So there you got the end behavior, right? Negative infinity here, plus infinity here, positive infinity up here, negative infinity up here, right? Yeah, very good, right? And again, you may say, right, Professor, we didn't use this, we didn't use it. You don't need it. The end behavior is determined by the first term. This is the whole idea, right? All right, now guys, something for you to practice on. I want you to catch the end behavior of these functions. I'm gonna do the first one, and I'm gonna let you do the second and the third, okay? For you to see that it's not really difficult. Suppose they say, okay, there is this function f of x equal 2x to the third power minus 2x squared plus 4x minus 5. Determine its end behavior in words right here, right? So quickly, you pay attention to the first term, this guy, right? 2x to the third, 2x to the third, right? And then you look at this guy is positive, right? The coefficient, the leading coefficient. And then you look at the exponent, the degree, right? The degree is odd, right? And I can see the students are already figuring this out. Jack, close, but I think you need a refinement. Let's try to remember what is this in the table, right? Remember, I have 4 scenarios. If the degree is odd, it's going to be a chair, right? A chair. But since this is positive, this time you have to take the chair that looks like this, right? The increasing chair from left to right, right? Increasing chair, it will resemble an increasing chair from left to right. And this clearly rises to the right and falls to the left, right? In words, they didn't use the arrow notation, right? So falls to the left and rises to the right. Yeah, I know it's very tricky to find it, but just be careful, right? Look, this falls to the left, matches with this part, and rises to the right, matches with this part, right? Yeah, great. All right, so try to do number 7 now, please. Try to do this, give it a shot. It's not that difficult. Again, just look at the first term. Hint, analyze this guy, right? The end behavior of this will be the end behavior of the whole polynomial function, right? Yeah, because the first term is the one that is actually the leader. Yeah, try to figure this out. Aha, I see students are figuring this out. Aha, very good, very good. Great, Hughie, Savannah, Jing, excellent, excellent, very good, guys, very good. Yeah, I see you understood this. Yeah, there are just 4 possible scenarios, right? They're on the table, but let's try to get them. We take the first term, right? This, right? We focus on this quickly. This is this, right? Now we analyze this and this numbers, right? So it's showing a negative coefficient, right? Negative. And it's showing an even degree, right? Degree. According to that table that I show you, this should resemble a parabola, right? A parabola. But this parabola, since this is negative, instead of opening upward, it will open downward, right? Remember the frown face, right? Negative, downward. So this falls to the left and also falls to the right, eventually, right? Yeah, great. So this is that. This is just that. And for, if you look at the choices, you will find out that this is it, right? Falls to the left, look, and falls to the right. The others, they say something close to it, but not exactly this, right? Yeah. Try to number 8 now, and we will move on, okay? So we're gonna do more now, number 8. Now try to figure out the end behavior of this function. And the hint, as usual, right? Look at the first term. Focus on this, right? What is the end behavior of this power function? Turns out that will be the same end behavior of the polynomial function, right? Yeah, very good, very good. Aha, Savannah, very good. Jing, good also. Good job, guys, very good. Yeah, very good, guys. So when you look at this, you quickly realize that this guy is negative, right? Negative coefficient. The K is negative, right? The coefficient. And then when you look at this, you see that the number 3 is an odd number, right? Odd degree, right? And we have a table with 4 scenarios. For odd degree, the graph should resemble a chair, right? A chair. But since this is negative, instead of taking the increasing chair from left to right, you take the decreasing chair from left to right, this one, right? And you look at the tip of these arrows, right? This one is saying rises to the right, to the left, sorry, left. And this is telling me that falls to the right, falls to the right, okay? So when you look through for number 8, then you have to pick this one, right? Rises to the left, right? This is stated here, and falls to the right, falls to the right, right? Very good, very good. And again, this all comes, guys, from this table, right, that you have in your textbook, or from the notes, you can copy and paste from there, right? This table, right? Depending on the exponent being even or odd, the degree, right? And depending on the coefficient, you have these 4 shapes, right? Parabola-like or chair-like. Great. Okay, so this is for power functions, right? What you have to do.